figures with you told me about Matthäus?
That's usually what I translate it to.
Okay, so probably Matthäus, or?
Yeah, that's close enough.
Okay, so
yeah.
Matthäus Wander is from the University of Duisburg, and we're moving from 1% to another, so this 1% is the NSEC, and he's going to tell us a bit more about that.
Yeah, the DNSSEC is another new protocol that has been around actually more than 10 years. That's the specification, the agency specification. So what I'm going to tell you about is measuring the adoption state of signed domains. But before that, I would like to provide you some fundamentals so that you understand how the measurement methodology works. So DNSSEC, what's basically doing is it's signing responses. So we have all those domain names on your domain name server, and they are now signed with RSA or another signing algorithm. So you query for an existing name like www.example.org and so on. You go to the server, and the server responds with, yeah, here's your resource record that you requested, here's a signature that you can verify it. And those signatures are pre-generated, so they are generated by offline signing, so that the server does not have to do online cryptography, because that would be expensive. That's the assumption behind it. So signing is expensive, we do it once, we put it on our server, and every time a client arrives and queries for a name, you can just get it from the database. Okay, so now what happens if you ask for a non-existing name, like for test, and there is no test here? Well, you can send a response, does not exist, but what do you sign? Do you need to use online crypto? Well, the DNS folks thought, no, we don't want to use online crypto, we want a method for offline signing. So they create a chain of all existing names, and what you get is an indirect proof of non-existent. You get a response where it says, there is an existing name NS1, there is an existing name www, but in between of those, in alphabetical order, there is no name. So your test name here does not exist. This is a proof for it. And it's signed, so you can verify it actually. So what you can do with this is now you can get a copy of the whole DNS zone, of the whole database. You just ask repeatedly for non-existing names, and you get one existing name after another. So you get a copy of the database. Now some folks said, sorry, we can't let you do that. We do not want to disclose our whole database. So they invented a new method. And they said, well, let's just put all those existing names into a hash function. We're hashing them, so we will get a chain of hash values. The order will change of them, so if you put FTP into a hash function and mail into a hash function, they will probably have a different order, but that doesn't matter for the non-existence proof. So you have a list or a chain of hash values, and you're doing basically the same, except not for cleartext names, but for hash values. So you're asking for a name test, and the server says, oh, sorry, it does not exist, because the hash value of test would be in between those two. We have a name which has this hash value, we have a name that has this hash value, but in between of those, there's no name. And you can verify it because you can compute the hash value of test, and you will see, oh yeah, it's between those two. So it does not exist. So what you can do now is you can get a list of hash values by repeatedly sending queries for non-existing names. And then, well, you could try to break the hash values, because hash values could be reversed to cleartext names. There are hash breaking techniques, but they are expensive. So what we need to know about the hash function is it's basically SHA-1. It's iterated SHA-1. You put in the domain name and the salt value. This is just an arbitrary string, but this salt value is identical for the whole DNS zone. So for a top-level domain like .org, they are using always the same salt value. So you know the salt value because your client needs to know it in order to verify the response. So you put in the domain name, you run SHA-1 over it, and you can repeat the process so that you increase the computational complexity. So it gets a bit harder to break those hash values, but it also takes computational power on the server. The server as well, the server operator will have to, every time there is a non-existing, a query for a non-existing name, will have to compute those hash values. Okay, so that's basically NSEC 3. And now we're going to exploit this by using zone enumeration techniques, and we'll be using this via NSEC zone enumeration over cleartext names and NSEC 3 zone enumeration for those domains that are using the NSEC 3 hashed proof of non-existence. So the question here is first, can we perform zone enumeration over all top-level domains? There are like 1,400 top-level domains, at least at that time of the study. And will it work for NSEC 3, or will NSEC 3 prevent this? And if we succeed, then we will get a list of all names that are assigned with DNSSEC. So then we can check and see what's the deployment state of DNSSEC. How many signed domains do we have? What algorithms are they using? Is this working? Can we actually validate them? Or are there any problems? So let's go into this. The measurement methodology would be this. We have a host, and we're sending queries to top-level domain servers, to all top-level domains. For NSEC, this will be basically everything that we need. For NSEC 3, we will also need some computational power. So we'll be using GPUs for that, because GPUs are really effective to break hash functions like SHA-1. And so then we will get a list for those top-level domains that are using NSEC. We will get a list of Cleartext names, Cleartext domain names, and we'll get a list of hash values. And then we can also use GPU computational power to break those hash values. Okay, so here's the result after running a zone enumeration over all top-level domains, over 1,400 top-level domains. What you can see is that they are not uniformly distributed, but there is one top-level domain which clearly stands out, and this is .nl, the Netherlands top-level domain. Around 40% of all DNSSEC domains are below .nl. And if we take a look at the top 10 domains, top 10 I mean by counting DNSSEC domains, not by counting all domains, only the signed domains. So we will see that 92% of all DNSSEC domains are below the top 10 top-level domains. Okay, so first there is this distribution. And now if we compare this to the number of domains that are not signed, by taking a look at the TLD operators on the website, they are providing statistics, how many domains have they registered. Not all of them, we cannot do this for all top-level domains, but at least those top 10 that we're seeing here are providing statistics. So now we can see .nl, .se, which is Sweden, CZ, which is the Czech Republic, they have DNSSEC adoption ratios around 50%. So half of their domains are actually signed with DNSSEC. And then we will see .com, which is by far the largest domain of unsigned domains. .com has more than 100 million registered domains, but the DNSSEC adoption ratio is very low, it's less than 1%. So actually this is all red and there is a 1 pixel of blue. Okay, so we have a very uneven distribution depending on what top-level domain you're looking at. Okay, so this is the number of all all second-level domains signed with DNSSEC. So it's a total number of 6.4 million DNSSEC domains, and this number is guaranteed to be complete because zone enumeration, once it has finished, gives us a complete chain, and it is guaranteed that every DNSSEC name will be included in this. And by saying that this is guaranteed to be complete, I mean that certain limitations apply. One of the limitations is I ran this measurement only over top-level domains. So this will be fine, like running it over .org, so we'll get names like example.org, iena.org, itf.org, or the hash values of these names. But there are certain top-level domains which are using a 3-level structure, like .uk, for example. So for .uk, we'll be getting names like ac.uk and co.uk, but what I will not see are domains on the 3rd level, like Aberdeen AC.uk or Google.co.uk. And this is a similar case for domains like Taiwan or Brasilia, which are also using a 3-level structure. So the domain count, the DNSSEC count for those top-level domains will be underestimated. So 6.4 million is actually a lower bound of DNSSEC domains. Okay, so now that we've retrieved a couple of Cleartext names and a couple of NSEC 3 hash values, let's try to reverse the NSEC 3 hash values to get the Cleartext name and to run additional analysis over it. So what we're doing is we've gotten from 1,200 top-level domains that are using the hashed approach, the NSEC 3 approach, We have gotten 5.7 million hash values, and now we're running a partial brute force and dictionary attack. Partial because it would be infeasible to run a full brute force attack. The names get longer and longer, and it will just take too much of time. So we cannot reverse all names, but we can try our best to reverse as many as possible. And this is run on 7 GPUs and 7 graphic cards for 2 weeks. I have a decent dictionary which we were then able to break around 80% of those hash values. So 79% or 80% of hash values have been reversed to the cleartext name. So this means that NSEC 3 actually does hide a few domain names, but only a minor portion of them. Only 21% were really protected by NSEC 3, and the other ones were revealed in cleartext. And for this protection, the server operator is paying because the NSEC 3 hashing, every time you're sending a negative response, you're saying does not exist, here are the hash values, the server has to compute a hash value, so there is additional CPU cycles burning for this. So the server operators are paying to protect those 20% of domain names. Okay, so here's the cleartext recovery ratio for the top 10 top-level domains. First of all, Sweden does not use NSEC 3. They're using the cleartext approach, the NSEC secure denial of existence. So for the Swedish top-level domain, you get a list of all second-level domains, all registered domains. They're fine with that. They are sharing it. You can actually access the zone file. You can request zone file access. For the other top-level domains, well, they are using NSEC 3, and we have varying recovery ratios, around 70%, 90%. So on average, it's 80%. You can actually request zone file access from a couple of these top-level domains, but not all of them. So with the NSEC 3 zone enumeration, you get access to domains that you wouldn't have been able to see otherwise. Okay, so what helps actually against zone enumeration, against NSEC 3 zone enumeration? There are two other limitations. First of all, for .pr, which is Puerto Rico, zone enumeration did not finish because they had a broken chain. It seems that they had a configuration error, and I was not able to figure out how to fix it on my side. And actually, I was not even able to figure out what the real problem was. It was really confusing. I didn't understand it. So they had a broken chain, so I couldn't retrieve the whole chain. So I retrieved like 80%, 90%. That's an estimation. I don't know really. But this is not a practical defense mechanism, because they are returning invalid queries, invalid responses. So for some queries, if a real client is asking and it's getting a response, it will be an invalid response. It will not validate. So this is not something that you can use in practice as a defense mechanism. Furthermore, there was another top-level domain, .by, which is Belarus, and they have been recreating their signatures every time with new hash values. They have every time updated the salt values, so this will give us new hash values, and they have done this every 10 minutes. So this means I had only a 10-minute window to run zone enumeration. And while this could be possible, this would mean I would have to send a lot of queries to the Belarus servers, and I didn't really want to do that. I had a rather low sending rate, query sending rate. So this means I wasn't able to retrieve the whole chain, but a malicious attacker could just increase the sending rate, and they could succeed. But this is something I didn't want to try. So this could be a defense mechanism, but I'm not sure about this. What is a defense mechanism is to do online signing, online cryptography. So every time you get a query for a non-existing domain, you return a response, and you create this response online. And it will have a signature and hash values which cannot be used to build a complete chain. So this is a real protection here. But this is expensive. Online signing for every query, every time creating a signature is expensive. And you can do this with either NSEC 3, or there is another mechanism, NSEC 5, which is a bit different, uses a different signing function, but it's still using online cryptography, so it's still expensive. So there is a protection, but it's very expensive. What does not help against zone enumeration is actually the mechanism that was supposed to help, which is the hash iteration count. If we take a look at the recovery ratios, of a few top-level domains that are using high iteration counts, 100 iterations, 150 iterations. This is 150 is the maximum for a certain parameter set. So this is specified as the maximum, depending on what parameters you use. But for this domain, it's the maximum. So you cannot use more than 150 iterations. And actually, it slows down the attack. My dictionary attack takes a bit longer. But whether it takes 1 hour or 10 hours, doesn't really matter. So in the end, we were still able to recover 96% of cleartext names. And the hash iteration count hasn't stopped us. On the other hand, if we take a look at those top-level domains where we haven't recovered so many names, like for example here, this is a Korean top-level domain. I don't know what this means. We only had 8% recovery ratio, but they were using only 10 hash iterations. So our dictionary was simply not good enough to break Korean domains. So it depends on the quality of the dictionary and not on the hash iteration. Okay, so now we've broken a couple of domains. So we have a list of cleartext domains from NSEC, where we have hash values, broken them, and now we would like to study those domains. So we're sending queries to get their DNSSEC configuration and DNSSEC parameters. Which algorithms are they using for signing, what are the public keys, and a few other parameters. So we're using a binary resolver for this, querying 5 million second-level domains now, not top-level domains, we're querying now second-level domains. And here are the results. For example, here is the distribution of signing algorithms. And what we can see is that 2 variants of RSA, actually both of them are RSA, are being used most frequently. So most second-level domains are using RSA as a signing algorithm. 92% are using RSA, which is a fine choice. RSA hasn't been broken if you're using keys that are long enough. But RSA produces quite long signatures, so the messages will be quite long. And DNSSEC is a bit sensitive to long messages because it's based on UDP. And if those UDP messages get too long, you run into fragmentation trouble and so on. So there is another signing algorithm, ECDSA, which is based on elliptic curves. And this hasn't been specified for a long time. I think it has been specified like 3 years ago or so. But the adoption has been growing. So it's now 8% of all second-level domains are using ECDSA. 2 years ago, this was like 0%. So it has been growing. ECDSA is it's getting more and more popular. What I now want to see is, do these domains really validate? Okay, they are using DNSSEC signing, but does it work? Because DNSSEC is said to be, well, to run into reliability problems. If you make a mistake with your signing configuration, clients won't be able to resolve your domain names because they don't validate. So I've checked how many of these 5 million domains actually do validate. And what we can see is most of them validate correctly. 22,000 did not validate correctly for various reasons. The most common reason is you're asking the server, please give me your public key. I need it in order to validate the response. And the server is saying, here's my response, there is no public key, I don't have one. So this means the client cannot actually authenticate, cannot validate the response. This happens in 90,000 cases. Another reason for responses that do not validate are expired signatures. They have a validity period, and if they are not renewed, well, then they are invalid. So you cannot validate those. And there was one case where the signature was ahead of time. So the validity period was in the future, and it does not validate because, well, it was not yet valid. Okay, but if we put this into perspective, we had 0.44% of domains that had validation errors, but there were another 0.48% that had generic DNS errors. Servers not responding, maybe fragmentation issues, I don't know. I didn't really look into what those generic errors were. This would just errors that you couldn't resolve domain names. This happens from time to time. Server bugs, responses were invalid, timeouts, whatever the reason is. So DNSSEC has been increasing the outages, but not excessively. It's comparable to the number of generic errors that you're getting anyway. And 99% of domains, this is a logarithmic scale here, 99% of domains have been working correctly, luckily. Okay, so to sum up, we've seen that DNSSEC signing is common, but only below a few top-level domains. We've seen that validation errors are rare, but still they are visible, they do occur. We've seen that NSEC 3 protects from the disclosure of names, but only a minor portion of names are not disclosed. And the hash iteration count is not effective to protect from this. And effective protection is expensive because that would be online signing, online cryptography. Furthermore, we have seen that zone enumeration is a useful debugging tool. We could have seen a couple of errors on live production servers. There was not only the Puerto Rican domain that had trouble, there were other domains. So from time to time we run into bugs, server bugs, and you can see this with zone enumeration. Furthermore, we have seen that because the measurement was limited on top-level domains, no enumeration only over top-level domains, this has given us an incomplete picture, unfortunately. So for future work, I would recommend to use instead another list. And my recommendation would be not only if you're running zone enumeration, but also if you're making latency measurements to top-level domain servers, trace route to top-level domain servers, whatever you're doing with top-level domain servers, consider instead using the public suffix list, which is maintained by Mozilla. It contains all top-level domains, and in addition, those second-level domain suffixes used by .uk, Taiwan, Brasilia, and a few others. So this will be probably a more complete picture. And this would be a takeaway which goes beyond DNSSEC, hopefully. So thank you for listening.
Questions?
So in the case of NSEC 3, how many queries did you make to the DNS server to reach a certain level of confidence that you actually retrieved all the hash values?
We only have to send one query to retrieve one NSEC 3 response, one NSEC 3 resource record. So we need to send as many queries as there are NSEC 3 resource records. Because you can select those query names by, you create a database like I've seen this NSEC 3 record goes from here to there, it goes from here to there. So you can then select the query names so you will send for those ranges that you haven't seen before.
Right, but I'm just curious, how many did you actually send to reach a certain level of confidence that you've seen everything?
Well, it's basically exactly like the number of DNSSEC domains. So let's go to this statistic here. For .nl, we needed to send 2.5 million, and then we had the confidence that we've seen everything because we had a complete chain, which goes from over all hash values.
Right. So wouldn't it be better to actually use a very extensive dictionary and query those top-level domain names for the actual response instead of going the inverse of cracking the hash values?
Well, the dictionary has way more names than 2.5 million, and you will get way more negative results, so where you haven't found a domain name. So you will need to send a lot more queries to the server. This will increase the load on the server, and this will take longer on your side, on the client side.
Did you see people were picking, was the choice of salts good, or did you see people using the same salt in different domains, or changing it infrequently, or anything like that?
Everything. So people were randomly selecting and changing the salt. Some people were had a random salt but haven't been changing it at all. And some people do not use the salt, so they use the salt which is an empty string length, like .com, for example.
Okay.
They use the most simple configuration that they could have thought of. They're using NSEC 3, but with 0 additional hash iterations, so it's only 1 hash iteration, and no salt.
Could you frustrate this by adding random records to a domain that were long and hard to crack, so that if you guess one, you get something uncrackable at both ends? And
you could do that, but you will still get those domains that are short.
yeah.
And these are the domains that you're interested in.
Oh, okay.
So I have a question. So my takeaway from this is NSEC is bullshit. Would you agree?
Is this being streamed?
So the reason for putting it that way is that passive DNS exists, right?
Yeah.
So you can just go and buy the list from Farsight or
You
other
get
classes of
pretty
DNS,
decent lists, yeah.
so
There are other ways to get it. Actually, there is some motivation behind this to use NSEC 3, but I'm not convinced by it, so I cannot convince you. Some top-level domain operators are saying it's private data, it's intellectual property, we cannot give it away because you could use it for spamming or whatever. So they have some argumentation which is not based on technical grounds, but more on maybe legal matters. I don't know.
But given that people there are passive DNS probes all over the place,
Yeah.
all of these names are known.
Yeah. Well, all or majority of them.
I mean, anything that gets used is known.
If you have a passive DNS sender in that network.
Yeah.
Yeah.
So okay, so we agree that NSEC is kind of, and I like this other nail in the coffin. Other questions? Okay, I have another one. So DNSSEC deployment is like, it's a small mission of work. And I've always been looking for reasons to encourage people to do this. And I was talking to a penetration tester who told me that he takes the existence of DNSSEC as a sign that the network is likely to be a bit harder to break into.
Okay.
Not because of crypto, because it just indicates a level of housekeeping.
Oh, okay.
Did you see any other characteristic of the signed domains versus non-signed domains that would be of interest?
No, I haven't been looking into that. That might be interesting future work to see who's actually using DNSSEC.
Yeah.
Yeah.
So I thought it was actually the best argument I've heard for DNSSEC is that it indicates you care about your domain, your zone file, and therefore the rest of your network is probably a little bit better.
There's actually a study from a colleague from TU Delft, Maciej Kuczynski, and I think he looked at the maliciousness of TLDs, and he found that domain names which have DNSSEC are a bit less misused by hackers.
Okay.
Just as an indicator that there might be, that they also take care about abuse detection in their own domains. So.
This is a presumption that is probably valid right now, but whether it will be valid in 5 years.
Yeah, sure. That's good.
Yeah. I mean, if you're in the 1%, then so they won't know they're backing it. Okay. Any others? If not, thank you again.